Alright, that worked. Cool. How is everybody? Some of you I haven't seen in like 45 minutes. Alright, well hopefully you've turned in your homework. So let's start with any burning homework questions, and as usual I'll grade them over the weekend and give you some specific feedback on Monday. If there's anything you want to know about before I grade your homework, go ahead and ask. Yeah, 3.3 is definitely a tricky one. Let's take a look at that. So, let's see. So construct the truth table for, okay, and I'm guessing people were probably good with that. So I'm just going to write down this this equation, and then we'll play with it. So P and not Q, or R and P. And then let me do this. All right. So supposing that we have a truth table, give an example other than X itself of a proposition equivalent to this. So how do we find equivalence? We use those identities, those laws of logic, to make rearrangements, throw in De Morgan's theorem, double negation, whatever we can think of. So what kinds of things did people try to turn this into a equivalent expression, usually a simpler expression?
I thought, since it had given an example of R and Q with like the money and doors, that we were supposed to actually write a propositional statement, not an equation.
Oh no, someone asked about that Wednesday, and we said go ahead and use equations.
Sorry.
That's okay. And that's not necessarily wrong to do it, but it's a whole lot easier to do it with equations usually. So somebody said use the truth table and came up with an equivalent. Somebody else said use involution and De Morgan's. So involution is double negation, right? So we can apply that where it kicks in. De Morgan's we know well. Let me see what happens if we just kind of distribute this. And I need to be really careful because my carets sometimes look like negations. But if I distribute this term against these two terms, I think I would get something like P and not Q, ORed with R, and then that whole thing gets ANDed with P and not Q, ORed with P. And so over here I've got P and something or P, right? Well, if P and not Q is going to be true, P has also got to be true. And so P and not Q or P, I believe this is logically equivalent to just P. And how would we see that? Well, we could distribute this P against here, right? This expression would be P and P, or P and P or P, and P or not Q. And so this is just P and P or not Q. I think I'm doing something weird here. Let's not trust my memory. Let's look at distribution. So P or this thing is P or the first thing ANDed with P or the second thing. So P or this expression is P ORed with P ANDed with P or not Q. P ORed with P is just P. So this is P ANDed with P or not Q. And we can distribute once more. If we do that, we're going to get P and P or P and not Q. Okay, that's not going to help us. So how do we turn this into P? Yeah, I'm going to go truth table. So P, Q, not Q is the complement. P ANDed with the complement, and that's the AND of these. So that looks like this. And then this column ORed with P. So this is a 0, 0, and a 1, and a 1. And this is exactly the same as P. There's a way to show that algebraically. I'm kind of spacing on it. So someone says they got that after distributing. Okay, cool. So this is the same thing as P. And that's certainly a simpler expression. So we could actually stop right here and say P and not Q, or R, and P. Well, that looks like a different, statement from our original proposition X, but it's equivalent, right? And it's equivalent because P is equivalent to that. And if we wanted to, we could continue this distribution. We can distribute P against these two terms, and this would be P and not Q, or P and R. And P and not Q is just P and not Q, or P and R. And then we could pull out a P and say this is P and not Q or R, which somebody posted in chat. But that's a much simpler statement than this, right? So this has a negation, two conjunctions, and a disjunction. This has a negation, one conjunction, one disjunction. So that's an equivalent. So let's go on to implication and implied by. So part C, give an example of a proposition that implies X. And we could work with the original X, or we could work with the reduced version of it. It didn't have to be simpler. It could be more complex. That would be fine. So an implication, proposition that implies X. So something which, if it is true, then X will also be true. So any ideas? So someone said R and P implies X. Well, if R and P are both true, if we just look at the simplified form, if R and P are true, well then this will be true, and this disjunction will be true, and so the AND will be true. And so if this is X, right, any time that this is true, we're guaranteed that that's true. So that would be a great example of a proposition different from X that implies X. This is not equivalent to X, though. Right? R could be false, but as long as Q is also false, this would be true, and P, if it's true, would make X true. So these don't have the same truth value in all cases. We're not looking for equivalence here in this part. We're looking for something that if it's true, then X is true. Right? So we're find some proposition A such that A implies X. In other words, if A, then X. And we're not finding something that's equal to X. We're finding something that if it's true, then X is true. So yeah, someone said they thought about this by asking, what would make the conclusion true if the hypothesis was true, but not necessarily the other way around? If the truth values vary in perfect unison, then they're equivalent. But let's see if I can do something. Let's see. I don't know if I can do that. Okay, here's a proposition. It is sunny or it is Friday. What's another proposition that implies that this is true? Well, the simple proposition, it is Friday. If it is Friday is true, then this is true. So we could say, you know, it is Friday implies that proposition. That's not the same as this. But if this is true, that is true. And yeah, someone asked, could it also be, in this case, not Q and P? Yeah, that would also work. So if not Q is true, and P is true, then this whole thing is guaranteed to be true. So the symbolic version is find a proposition A such that A implies X. Alright, the last part is a little easier. Give an example of a proposition other than X that's implied by X. So find a proposition D such that X implies D. So find a proposition that is guaranteed to be true if X is true. Well, X is a conjunction of P with not Q or R. So if this thing is true, we know, for example, that P must be true. Right? Because if P was false, this would be false. So we can actually write X implies P. We could also write X implies not Q or R. We could also write X implies not Q and not R if we use De Morgan's. And there's things like that. We could be a little silly and we could say X implies X or, you know, W or Z without even knowing what the propositions W are or Z are. Right? If X is true, then certainly this proposition is true also. And it's not equivalent to X, but it's implied by. All right, and someone asks, what's the protocol for using this class in Discord? You know, I want students to collaborate on the material. Right? So I don't understand what an implication is, or I don't understand why, you know, 3 of the rows in an implication truth table are true. Or I don't know what implies versus implied by means. Discussing the concepts, great, right? Go for it. Discussing things that we've talked about in class, great, go for it. I guess what you don't want to collaborate too closely on, though, is actually working on solutions to specific problems. So, you know, I wrote this down, but I don't think it's quite right. Oh yeah, I did the same thing in the beginning, but I changed my proof here. That's probably too much collaborative work for homework. And we don't get as edgy about you know, plagiarism in homework as we do on turned in assignments or tests. But you want to make sure that you're figuring out as much of the stuff as possible. And if you're stuck, if you're not sure, you know, how to get to the next step, get across the bridge in a proof or something, you want to ask for help. And, you know, you can definitely ask me. You can come to office hours. You can ask in class. But you can get some help from classmates on Discord. And I encourage brainstorming, kicking around ideas, and so on. Just make sure that you're not, you know, actually sharing solutions to homework questions. You can pose similar questions and talk about those. And there's also a slew of questions in the textbook. Right? So I give you even numbered questions, but the odd number questions, there's answers in the back of the text. And those are great to work on. And if you want to actually work, you know, in great detail, collaborating with one another on those, that's totally fine. So hopefully that makes sense. Cool. All right, other questions? I might have missed some earlier in chat. Yeah.
So
this is still wrong with this.
Say again?
This is still, like, questions about homework.
Sure, or anything else.
So, I'm just, hang on a sec.
Mm-hmm.
Section 1.5, number 2, part D, where it asks us to calculate the series from n equals negative n to n of k, or n equals 1, 2, 3, 4. Yeah, so part D, number 2.
Mm-hmm.
I got all of those were equal to 0, personally.
Sum from I equals 1 to 5 of 20?
No. Part D, as in delta.
Yes, so sum from k equals minus n to n of k.
Is it?
Yeah, so these are 4 separate questions, so let's do n equals 1 first. Sum from k equals minus 1 to 1 of k. Well, that's negative 1 plus 0 plus 1. That's 0.
Wait, what?
So let's do the question where n equals 1.
I'm sorry. Okay.
Right? Let's do the question where n equals 4. You're being asked to find the sum from k equals negative 4 to 4 of k. Well, set k equal to negative 4 and write down k. Set it to negative 3, negative 2, negative 1, 0, 1, 2, 3, 4. Add those all together. And you still get 0. So yeah, those cancel in all cases. So each of those 4 summations is equal to 0.
Okay, I read it totally wrong and did it wrong, so...
Okay.
Were we planning on going over this summation proof at some point in, what is that, number 4, I believe in also that same section?
So, so as I said last time, this is a verify, right? So it's not asking for a very rigorous proof, right, that this is true in general. It's asking you to look at particular values of n, right? In this case, n equals 3. And so yeah, let's just look at part A. So let me write this down. All right, so I think that's what it's asking us for. And so, what do? We take this and we start doing some things to it that we know are legal, and we hope that as we do that and we write this in different forms, we eventually write it in a form which looks exactly like this. Okay? That's a preamble to how we're going to do most of our proofs in this course. We're going to try to show that, you know, something's equivalent to something. We're going to start with the first thing, do legal things to it that don't change its value, and hope we end up with what we're after. So, what does it mean to say the sum from I equals 1 to 3 of some expression? It means write this expression for I equals 1. Write it for I equals 2. Write it for I equals 3. And add them up. So this is mechanically what this summation symbol means. It's a shorthand for this expression. And A, B, and C, it doesn't tell us, but we can assume they're just plain old numbers, which means that the order in which we add doesn't matter. It's associative. So we could just write this as A1 plus B1 plus A2 plus B2 plus A3 plus B3. And we also know that addition is commutative. A plus B is equal to B plus A. And if we generalize that, we find that if we have a bunch of things added together, we can rearrange them in any order that we like. And this doesn't work with subtraction, but it works with addition. Addition, we can rearrange the order. So I could write this equivalently as this. And we'd have to agree this is the same thing as that, which is the same as that, which is the same as that. Well, I have a shorthand way of writing this sum. This is the sum from I equals 1 to 3 of AI. And I have a shorthand way of writing this. This is the sum from I equals 1 to 3 of BI. And I just have to add those together. And so there I've verified that this summation is equal to the sum of those two summations.
So you said the commutative law would have been necessary to do this correctly. Where would you label the commutative law?
For verification, I wouldn't worry about it too much, but I would say, you know, here, associativity of plus, and here I would say commutivity of plus. We're skipping a bunch of steps. Right? Commutative basically says x plus y equals y plus x. So really, to show that this is equal to this, here's what's really happening. Well, I can apply commutivity to these two things and say this is A1 plus A2 plus B1 plus B2 plus A3 plus B3. And I can think of this as B1 plus B2 plus A3 by associativity. And then I can apply commutivity to these two terms and say this is A1 plus A2 plus A3 plus B1 plus B2 plus B3. And then I can get rid of those parentheses because the order doesn't matter. And then I can bring in associativity in again and say I'm going to get the same thing if I add my A's together first, and then I add my B's together, and then I add those two sums together. And then this is, you know, that first summation plus the second summation. So really between here and here, there's a whole bunch of steps going on. But, you know, if it says verify, and it's a homework question, right, it's probably plenty just to say, you know, I'm using associativity, I'm using commutivity. But for integers, for real numbers, we kind of take it as understood that, you know, 2 plus 3 equals 3 plus 2. And we don't have to formally state that. It kind of depends on the level of rigor that you're after. This is not a math course. And so we'll get more relaxed in some cases. But in some cases, I will ask you to be extremely rigorous, particularly when we're doing proofs when we come back to mathematical induction. We'll be looking for a lot of rigor, but I'll make it clear like when that's the case. Does that help?
That does. There's a lot of discussion on 3.3, number 6, though.
I'm just catching that right now. So hold on a second. Let me pop something up over here on the side. This is good because you spend time on the homework questions, and I want you to like get some benefit out of that.
Yeah, okay, that was the wrong time for my dog to shave.
I hope I got benefit because I don't think I got any points.
Oh, you always get points, right? There's tons of
Maybe a few.
partial credit. All right. So which question we're looking at? 3.3.
Number 6.
Number 6. It's the last question on the homework set, so it's got to be a good one. Find a proposition that is equivalent to P or Q and uses only conjunction and negation. That's a great place to throw out De Morgan's theorem. Because what does De Morgan tell us? It tells us that the negation of P or Q is equal to the negation of P ANDed with the negation of Q. Right, so that's classic De Morgan's. And if we negate both sides, this will tell us that P or Q is, let me say, logically equivalent to the negation of P ANDed with negation of Q. And so there's an expression using conjunction and negation that's logically equivalent to conjunction or disjunction. De Morgan's return that
I
as
personally read that as you could only use the conjunction and negation laws. So I thought you couldn't use De Morgan's law.
Oh no, it wants a proposition that is equivalent and uses only. If it had said, write a proof showing something and using only conjunction and negation, then it might be saying, only use those laws. But the proposition should only have conjunctions and negations in them. I'm not grading that question anyway. But yeah, so that's a little ambiguously worded. How many problems did you say you grade on each homework assignment? I guarantee to grade at least one. Your next homework assignment, which is a bunch of proofs, I will probably only grade 1 or 2. But on these earlier ones where there's more questions, I'll probably grade more than 1 or 2. But I'll try to glance at all of them and get a feel for how people are doing. And if I'm only grading 1 or 2, I shouldn't tell you this. If I'm only grading one problem on the set, let's say I'm going to grade, problem 7, and you didn't do problem 7, I don't automatically give you a 0. If you did like every other problem, but you skipped that problem for some reason, I'll probably pick an equivalent problem and grade that one instead. But don't count on that. Don't use that to start doing half homeworks. But I try not to be like totally draconian about this. Let's see what else on here. I can open my camera because I'm done eating my lunch. I didn't want you to have to watch me eat lunch. Yeah, the only time I got sent to the principal's office in high school was in my math class, because I would wait until the teacher announced which question he was collecting, and then I would do that question really quickly. And I'd always sit in the middle of the room, so no matter which end they started at, I'd have enough time, hopefully, by the time the teacher got to me, that I'd have written up the question. But obviously the teacher knew this, so he said, okay, today we're going to collect question 17, and let's start in the middle of the room today with Nick. And I was like, I don't have my homework done. So he sent me to the principal's office, which tickled the principal. He was like, hey Nick, can I help you with something? So I won't do that to you. Yeah, it was a good lunch. There was some green veggie curry, which was nice. All right. Other questions? All right, good deal then. Are we week 2 or week 3? I've been thinking it's week 3, yeah. That's very weird. All right. Let's go on with looking at proofs. So I'll post your next homework assignment on Monday, and you'll have a week to do it. It'll be due a week from this coming Monday. So I'll post that up next week. So we've been using these laws of logic to show equivalence of statements and analyze propositions defined with these operations. That's kind of the backbone, the mechanics of what we're going to do next, which is looking at proving kind of more general statements. And so we're going to talk about rules of inference. This is the fun part of all of this, okay? So let me give you an example. So here's a proposition. If it's Friday, then I'm happy. Here's another proposition. It's Friday. Two propositions. We have no way of knowing the truth value of these propositions. Nobody really knows if it's true that if it's Friday, then I'm happy. I don't even know that, because I might have a bad Friday sometime, you know. Or maybe I'm secretly unhappy on Friday because I miss teaching my classes over the weekend, right? This could be true, this could be false. It's a proposition. We don't necessarily know the truth value of that. It's Friday. We don't know the truth value of that, right? I mean, we can look at the calendar and it'll tell us it's Friday, but maybe it is, maybe it isn't, right? We can write propositions and not necessarily know the truth value of those propositions. So the question is there anything that we actually know the truth value of? And it's a bit of a philosophical question. The universe is a lie, so if that is a true proposition, we quickly get into like the liar's paradox. So we may not know the truth value of this, we may not know the truth value of that, but there is something that we absolutely know. We absolutely know, guaranteed, if this proposition is true, and if this proposition is true, then the following proposition is also true. I'm happy. This is kind of subtle. we're not claiming this is true or false. We're not claiming this is true or false. What we're claiming is if this is true and if this is also true, then that is true. So we're going to be writing things like this. Some proposition P1, P2, P3, down to Pn, and then we're going to draw a horizontal line, and we're going to write some proposition Q. And this is the way we write proofs in propositional logic. And the way we interpret this in words would be like this. If P1, P2, up through Pn are all true, or each true, then Q is also true. So writing propositions one under another with a horizontal line and then a final proposition below the line is a shorthand way of writing if all of these things above the line are true, then this thing down here is true. And that's guaranteed to be correct. Right? When we write this down, we're saying this is a valid thing that we've written. Right? It is in fact the case that if all of these things are true, then Q is also true. So our goal in doing proofs is to confirm that this is a valid thing that we have written. To confirm that if all of these things are true, then Q is also true. And we do this by using these laws of inference, these implications and equivalences. And they have very fancy sounding names, but let's just start with the first one. This is called detachment. It's sometimes called direct reasoning. And it basically says, given this, if P then Q, and given this, P, we can conclude Q. Now this double arrow is really just an implication. It's an if-then. But the double arrow saves us from having to write a lot of parentheses. It says everything on the left of the double arrow is the hypothesis. Everything on the right is the conclusion. And that's really important. YouTube won't let me tag with arrows. When we see something with a double arrow, so we see some left-hand side, double arrow right-hand side, means if the left-hand side is true, then the right-hand side is true. Page 57 and 58, 58 and 59, I think. 59 is the one we're on right now. All right, so be really careful when you're working on these things. You'll see things like, you know, P and Q or not R implies S. Right? So this is a little ambiguous, right? Is it P and Q or not R implies S? Or is it P and Q and not R implies S, right? So we could put in parentheses. When you see the double arrow, it's unambiguous. It really means P and Q or not R implies S. All right. So what's the first rule of logic that we have here? It's called detachment. And this is, you know, it's Friday and I'm happy. So this says if P then Q and P implies Q. If we were to write this in that proof notation, which is in itself a proposition, if we were to write that in that proof notation, we would do it as follows. P arrow Q, P, therefore Q. And this is guaranteed to be true, right? Because what does it mean when we say that if P then Q is a true statement? Well, it means if P is true, then Q is true. Now, if you also turn around and the next thing you say is, oh, and by the way, P is true, well, you just told me if P is true, Q is true, and then you told me P is true, I've got no choice but to conclude, hey, I guess Q is true also. That's what this is saying. Alright, so that's detachment or direct reasoning. And there's a series of rules like this. The next one is indirect reasoning. So if you tell me that if P is true, then Q is true, and you also tell me Q is false, I can conclude that P must be false. Why? Because if P was true, this thing you told me would tell me that Q is true, but you just told me Q is false. So P's got to be false. Disjunctive addition. This is making something more complex. If P is true, then guess what? P or Q is also true. So P gives us P or Q. Well, how does that work? Let P be the proposition, my name is Nick. Let Q be the proposition, the moon is made of cheese. So this says, if my name is Nick, then either my name is Nick or the moon is made of green cheese. Well, that's clearly a true statement because P is true. My name is Nick. So we can add extra things through disjunction. So that's disjunctive addition. Conjunctive simplification goes the other way. If you know P and Q are both true, then you know that P is true. If my name is Nick and today is Friday, then you know my name is Nick. If my name is Nick and today is Friday, you know today is Friday. We can do a disjunctive simplification. This one's a little trickier. If we know that P or Q are true, one of those is true and we know that P is false, then Q must be true. Why? Because this part tells us that one of these must be true. This tells us it's not the first one, it's got to be the second one. And we can do that in two versions. Here's the good old chain rule. If P implies Q and Q implies R, then P implies R. If it's Friday, then I'm going to teach. If I teach, then I'm going to need more paper. So if it's Friday, I'm going to need more paper. Conditional equivalence, we looked at this when we first looked at conditional statements. And this is a you know, this implies that, and that implies this. So it's a pair of statements, each implying the other. Biconditional equivalence is using conditional equivalence in both directions, so that's just expanding this out. And contrapositive, we've looked at if P then Q is the same as if not Q then not P. And these we don't get into as much. These a lot of people seem to gravitate to because people don't seem to like conditionals sometimes, and it gets rid of that conditional. But if you keep the conditional, you have the power of all of these things at your disposal. So what the heck do we do with these things? Well, we can prove propositions. And we know we can prove propositions using truth tables, right? But that's not always a good solution. So let me give you an example of a proposition. Given A, and given if A then B, and given if B then C, etc., and if F then G, I can conclude that G is true. It takes about 7 lines of proof to do this, right? Because I know if A is true and if A implies B, then I know that B is true. That's direct reasoning. And if B is true and B implies C, I know that C is true. That's direct reasoning. And after about 7 of these statements, I'll have proven that G is true. If I do this with a truth table, I've got 7 variables, A, B, C, D, E, F, G. That's going to be 128 rows in my truth table. That's a lot of work. So it's important to be able to use these laws of logic and these rules of inference to demonstrate things. I don't have my countdown running. Okay. All right. So let's do an example. Let's see, I've heard once that you don't really learn anything by exhaustive proof, at least not the same way as if you use the laws. Well, that's probably true. If you do a truth table proof, it doesn't usually give you any insight into what's going on. And, you know, computers are great at doing truth table proofs. 7 variables, 128 rows, not a problem, right? But I would argue that in most senses of the terms, computers don't learn anything about doing proofs by exhaustively exploring all rows of a truth table. Although that's an open question. All right, so let's do an example. So I'm going to write down some propositions that I'm telling you are true. Okay, if you send me an email, then I'll finish my homework. If you send me an email, I'll finish my homework. If you don't send me an email, then I'll go to bed early. If I go to bed early, then I'll wake up refreshed. therefore, if I don't do my homework, I'll wake up refreshed. And we're asked to prove that this is true. Okay, that what is true? We're asked to prove that if this is a true proposition and this are true propositions, then this is also a true proposition. In other words, if this happens, if this is true, 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 then this is a true proposition. Meaning, if I don't do my homework, I'll wake up refreshed. And if you think about it, you can probably convince yourself that it's true, but it's a little strange, right? There's nothing in here about if I do or don't do my homework, right? But we're concluding that if I don't do my homework, something magical is going to happen. I'm going to wake up refreshed. So we can try to prove this using propositional logic. So let's write some propositions. So let E be the proposition. You send me an email. Let H be the proposition. I finish my homework. Let B be the proposition. I go to bed early. Let R be the proposition. I wake up refreshed. All right, so this is like that homework exercise where you had compound propositions and you're trying to break them into smaller pieces. I want to write these statements in the language of propositional calculus, and I want to try to use these to prove this last statement. That would complete my proof of this. But I can't do that with words. So I'm going to try to replace these words with symbols, and instead of making, this, P1 is the proposition, if you send me an email, I'll finish my homework, I'm breaking it into smaller pieces. So using these definitions, somebody tell me, how can I rewrite this first proposition? If you send me an email, I'll finish my homework, and you can post it in chat or mic it if you like. Well, it's hard to mic because it's symbolic, but you can post it into chat. If you send me an email, I'll finish my homework. E implies H. All right, what about if you don't send me an email, I'll go to bed early? So negation of E implies B. All right, I think you got the idea. If I go to bed early, I'll wake up refreshed. Good. Therefore, and this line basically means therefore, right, which is what the 3 dots are. If I don't do my homework, I'll wake up refreshed. So negated H implies R. Uh-oh, here's the propositional calculus police. Okay, so now our task is to prove this. So yeah, that horizontal line we read is therefore. All right, how the heck do we do this? It's another puzzle. We play around with it. We apply laws of logic or these implications, and we see if we can turn this into that. And we're going to write down propositions, and every proposition we write has to be true. And additionally, we need to explain on the side next to each proposition why that proposition is true. And we're going to number these propositions. So there's my official proof beginning wavy line. All right, so I'm going to start off with a first proposition, 1. So is there any ideas here for anything we can do involving, you know, some of these things, or maybe laws of logic, to do some kind of manipulation on these? And somebody says chain rule sticks right out. And I can see that. I mean, we have an E here, we have a not E here. We don't really know anything about putting those. There's an H here that doesn't pop up until the very end. But this thing implies B, B implies that thing. That just kind of screams out chain rule. Put those two together. All right. So, man, I got something weird. Okay, here's a really important thing to keep in mind about proofs. When trying to do a proof, when trying to demonstrate something in this class, there's sort of 3 pieces to it. The first piece is making sure you understand what you're being asked to show. And that's kind of the most important, because if you prove the wrong thing, right, you don't get a whole lot of credit for it. So make sure you understand what you're being asked to show. And in this case, you know, if you've got it down to here and this is correct, this is pretty straightforward. We're trying to show not H implies R. Okay, the second thing, which is perhaps the most difficult, is figuring out why this is true. It's sort of seeing in your brain a series of steps that will get you from these 3 things to that. Okay, this is like a chess puzzle. You're trying to like checkmate the opponent's king, right? And you're looking for a series of moves that will cause that to happen. And that's where you need the inspiration, that's where you need the scratch paper and the trial and error and so on, until you've got the path. You see, you know, a series of steps that will get you from these to that. Okay? That's the real core of the work. But there's a third piece, which is you have to write it down in the proper format. Right? If you're playing chess and you suddenly see how to checkmate your opponent, you can't just reach across the board and knock their king down. Right? You've got to proceed step by step. So the third part, and the part where most students lose points on proofs, is formally taking what you've discovered in step 2 and presenting it. And this third part is all about the presentation. And it's especially hard if that second part came quickly to you. If you suddenly see why this is true, it can be hard to back up and think about how to describe in small steps the fact that this is true. So we're going to spend a lot of time writing out proofs in this level of detail. And so we'll start with the chain rule. All right. Well, I want to put these together and these together, but I can't just say not E implies R. Because, you know, my proof starts here. Why would that be true? Well, because I got this and I got this and I use the chain rule. You got to spell it out. So the first thing I'm going to do is I'm going to write down not E implies B. Now I know that's true because when I read this problem, it had these things and then a line and then this thing, which means if you assume these things are true, prove that that's true. So how do I describe that? My reason for this is simply, this is a hypothesis. So someone said, what about not E implies B implies R? We still need to start off with you know, things that are true and explain why they're true. And we actually don't have a notion of this. I don't think we'll ever actually encounter that. Now, if we threw in some parentheses, we could, but that's not what we would mean. What we really mean is what we're really after is, you know, that first thing implies a third thing. So here's how we can put that together. Step one, we write down this hypothesis, not E implies B. Okay, so we know this is true because it was given to us as a hypothesis. Step two, I'm going to write if B, then R. Why is that true? That was also a hypothesis. All right. Well, I've written two things that are true. They're true because they're hypotheses. And I have this rule of logic called detachment. Sorry, called the chain rule, which says if P implies Q and Q implies R, then P implies R. Well, I've been told not E implies B and B implies R. So what can I write down now? I can write down the following. Not E implies R. And the reason for that is I use the chain rule on statements 1 and 2. Where did what and come from? Oh, so in here it's saying if this is true and that is true, then this is true. And when we write a proof, having gotten to this stage of the proof, I've asserted this is true and this is also true. And so the chain rule says if I have this and this, then I also have this. And so now I have three things that are true. Okay, let me try to head off a common error. So a lot of times, I don't know why, I don't know where this is coming from, but at this point I see students do the following. They write this down as their third statement. And that's a true statement because of the chain rule. But it does not help your proof. All you have said is if this is true and this is true, then that is true. This is not the same thing as saying this is true. This is a much more powerful statement that you can actually use in your proof. This I can write down without knowing anything. I could have made that the first line of my proof and it would still be perfectly valid. So don't write down the statement of these rules. Don't repeat these things in your proof. You don't have to. You can assume the person reading your proof knows and believes these things. So they know this and they know that and they know the chain rule. Now, your proof is not wrong simply because you write a chain rule, but it's not the same thing as actually writing this. And if you write this down, you can't use this until you apply this to 1 and 2 and then write down this. So be really careful about that. All right. So this is a valid statement, right? Because I applied the chain rule to these two. All right. What do we do from here? What can we do for a fourth step? Direct reasoning. What are we going to directly reason? Or indirectly? Not E implies not H. E implies H and H implies R. Not H implies R. Somehow, right? So somebody said in chat, not E implies not H. It's almost right. Contrapositive, cool. What should we take the contrapositive of? All right. So someone's saying take the contrapositive of E implies H. In our heads, if we do that, we're going to see H implies not E, and here we've got a not E implies R. Maybe we can chain rule those. All right, so how do we do this? We can't just write down not H implies not E, because that's only true if E implies H, and we haven't stated yet that E implies H. So we've got to write that down. If E, then H, reason, hypothesis. Now we can say not H implies not E, reason, contrapositive, applied to proposition 4. Yeah, you definitely have to label every single line. So that includes hypotheses. So your goal is, you hand this to a judge and say, here's my proof that not H implies R. The judge doesn't want to do a homework problem. They want to read this and be convinced when they get to the end of it that not H implies R. And if you don't give a reason, they've got to figure out, so why does B imply R? And they've got to look around and look at the original problem and say, oh, it's up there. So you're spelling everything out, right? I'm the judge, I'm lazy. So you're putting it all down for me so I don't have to think. All right, and then someone said chain rule again. Back on the chain rule. So what's the chain rule say? It says not H implies not E implies R. We can put those together and say not H implies R. And the reason, chain rule, where we used proposition 5 and we chained it with proposition 3. And again, I'm not going to write down not E implies R, not H implies not E. I'm writing down the proposition that is new information here, and I'm explaining where I got that from, which was the chain rule, and I'm referring to the two pieces that I put together in the chain rule over here in the explanation. And then we write QED, perfect. Because that's what we were asked to prove. We were asked to prove not H implies R, and we just demonstrated that that is true. That's the end of our proof. Yeah, I was just saying which statements we were chaining. Cool, perfect. So now we could go back and we could say we've proven, not H implies R, which means if I don't finish my homework, I'll wake up refreshed. And yeah, that's what we were asked to show. But we usually don't go back to this. We take this and we turn it into this, and then we prove this, and that's pretty much the end of the proof. But if you're arguing with a friend, over dinner and you want to convince them of something, you go through these steps, and then you go back and you plug in the words for the propositions and, win your argument. All right. So that's a lot of talking about something that ended up being, half a page of work. Like I say, a big part of the challenge, points wise, is doing the presentation in a way where everything is labeled, everything you write down is true, and there's an explanation why each of those things is true. But there's the part that you don't see in here, which is figuring out, if I do a contrapositive here, that will set me up to do a chain rule, right? So it's looking a couple of moves ahead. You don't have to explain to somebody why you decided to do a contrapositive here. Maybe your astrologer told you to do it. That's totally legitimate, right? You don't need to explain why you decided to do this. You just have to justify why this is a true statement. That's what you're putting over here. Because I'm a Virgo. I'm a Virgo too. Yeah. In general, it may be best practice to always make a proof as short as possible, but I am absolutely not going to be grading you on that. But if you're don't try to do this on your homework that you're writing up neatly with no scribbles and things like that. Do this on scratch paper or a whiteboard or a boogie board or something. And sometimes it's useful after you've got a proof to go back and try to tidy it up. Because, if you're doing this while you're thinking of things, you might go down some paths that don't lead you to where you're trying to get, and so you back up and you go somewhere else. So you can end up with extra things in here. It's not a bad idea to go ahead and leave those out. And that can help you feel better about your proof when you're done too, right? If you go back through this and you look, it's fairly straightforward how to get from these to here. If I've got 5 or 6 other statements here that I didn't use, like I took the contrapositive of this one also or something like that, right, then it's a little more confusing.
So how would you rather that we like write down if we had this on homework, how would you rather that we write it down on the submission?
What do you mean, how would I rather you write it down?
Like if you don't want us to write down how we worked it out, if we did this exact same thing, sort of like on our scratch paper,
Mm-hmm.
and that's how we worked it out, then how do you want us to write it?
So this would be what you would want to turn in, right? A statement of what you're trying to prove, and then a series of propositions with explanations for why they're true, leading up to the thing that you're trying to show. Does that...
Along with something that identifies what each symbol or placeholder is representing.
So if you're starting with a word problem, then yeah, you need to start off with what these variables represent, right? And then write down, what it is you're trying to prove based on the original problem. And then from there, go down and write a series of propositions with justifications for each of them.
Yeah, that makes sense.
Say again?
I said that makes sense.
Okay, good. And I suggest don't try to type these up. Write them out by hand and scan them, right? Because if you use an equal sign instead of an arrow, it can get confusing. And I want you to get in the practice of using these symbols, because you're going to see these a lot. And the more that you work with them and write them, the more you're going to be able to understand them when you see them on tests and such. So unless you like doing typesetting and using these actual symbols, I'm going to ask you to actually write these out by hand. And I'm thinking the midterm, I'm going to go towards having you actually write up on paper your answers to the midterm and then sending in a scan rather than trying to type them in Canvas. I haven't decided yet, but I think that's the direction I'm heading in. But I'll decide in the next week. All right, well, we got 2.5 minutes left, which I don't want to start another proof. This is probably a good place to call it quits for the week. So we'll spend next week looking at a few more examples of using proofs, and then we're going to switch gears. So we'll do that, and then we'll start in on some number theory, and then we'll come back to this and look at induction. And yeah, if I decide I'm going to have you turn in scans or turn in PDFs from things that you write. If you decide to type, right, you can just export your document as a PDF. It doesn't have to be handwritten, but I may ask you to submit a PDF with your answers for the midterm. But if you like typing and you've got ways to do that, that's totally fine. You can just export as a PDF. All right, cool. We are out of here. Have a good weekend. Enjoy the sun, and I will see you next week.